Okay guys, welcome to section 9.3, geometric sequences. So we begin talking about patterns of numbers and sequences, and a sequence is a list of numbers. In the last section we looked at arithmetic sequences, which we could add a common number to a previous term to get a new term. In this section we're going to explore what happens when we multiply a number to the previous term and to get to the next one, and that's called a geometric sequence. So our essential understanding is that the ratio of any term after the first to its preceding term is constant. So meaning if we take a number and multiply it by its previous, and then we keep doing that, we should get the same result each time. Okay? It's also important to notice that we can model geometric sequences explicitly and recursively as well. So what is a geometric sequence? A geometric sequence with starting value A and common ratio R is a sequence of the form A is the first term, comma, A times R, comma, A times R squared, comma, A times R cubed, and so on and so forth. The two rules that we have are explicit and recursive. Explicitly, we take A sub 1 times R to the n minus 1, and n has to be greater than or equal to 1. Recursively, we still define the first term, and we also say the previous term times r. And I want you to note that just because we're raised to the n minus 1 here does not mean that's the previous term. The a sub n minus 1 means previous term. So just be very careful when you're defining those geometric sequence rules. In our first example, we're going to look at two sequences and determine which is geometric and which is not. So, we're going to determine, we look at each one of these and we see that the first sequence is 3, 9, 27, 81. And when we look at that, the next term is always found by multiplying the next term, the previous term by 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. If you go reverse and we think about a ratio, you think fraction. 81 divided by 27 is a third. 27 divided by 9 divided by 27 is a third. 27 divided by 81 is a third. So, times 3 multiplying by 1/3, that ratio is constant. So we know that this actually is geometric. In this case, the ratio we're looking at is 3. Okay, so it depends on the which numbers you're dividing, but if we go 9 divided by 3, we get 3. 27 divided by 9 is 3. 81 divided by 27 is 3. That number is constant. You're not adding, you're multiplying. So because we have to multiply, we get a geometric sequence, and the common ratio now is 3. So that's geometric. 4, 8, 12, 16. Okay. Now each one of these, it looks like 4 plus 4 is 8, 8 is 12, 12 plus 4 is 16. So I try to multiply the first one. 4 times 2 is 8, but 8 times 2, does that give me 12? It doesn't. 8 times 2 would give me 16. So I just put question mark, question mark. These aren't all the same. The ratios are not all the same. And if that's the case, you don't have a geometric sequence. This would actually be arithmetic because you take the previous term and add 4. So that's not geometric. In example 2, we're going to write two rules. We're going to write a recursive rule and a explicit rule for a sequence given. Okay, so let's write these sequences. I'm going to start with the explicit formula. Now I know that I see 45, 90, 180, 360. And it looks like my ratio is going to be 2. 2 times 45 is 90. 90 times 2 is 180. 180 times 2 is 360. So my R value, my common ratio, is 2. Putting that into our formula, A sub n equals your first term times your ratio raised to the n minus 1 power. So we have A sub n equals 45 times 2 to the n minus 1. You can check that to see if you're right. The second term is 90. So A sub 2 is equal to 45 times 2 to the 2 minus 1 power. Well, 2 minus 1 is 1. 2 to the first is 2. 2 times 45 is 90. So we get that right result. Now, the recursive formula, we have to define two things. Well, we got to find two things. We got to know our first term, and then we got to write our rule using the previous term. First term is 45. To get the rule, we have to simply take and look at our previous term, and how do we get the next term? Well, to get 90, we take our previous term and times it by 2. And so that's what we do. The previous term times 2, where 2 is our common ratio. So that's an explicit and recursive formula for a single geometric sequence. In problem 3, we're going to be looking at finding the 10th term of a geometric sequence. Now, I've only been given 3, 2, 4, and 8. So to me, using a recursive formula doesn't make sense. We're going to use an explicit rule since we don't have a sub 9. In order to use the recursive formula, remember, we need to know the previous term. So I need to know a sub 9. And I don't feel like going all the way out to 9, because if I do, then I can just go out to 10 and not even write the rule. So explicitly, we have a sub n equals the first term times the ratio. Again, I stick with 2 in this case. So our ratio is 2 to the n minus 1. We want to know term 10. So n is no longer n. N is equal to 10. So a sub 10 equals 2 times 2 to the 10 minus 1 power. So that's to the 9th. So you have 2 times 2 to the 9th, or 2 to the 10th, which is 1024. So when you're looking for a specific term, if the pattern's easy, you may want to do a recursive formula, but if you go out past 5 or 6, then generally writing an explicit rule is a little bit easier. Our last problem deals with geometric mean. When we talk about geometric mean, we're talking about an average, like arithmetic mean. So in this example, we're going to find the missing term. So again, I have 4, comma, blank, comma, 16. This is geometric, so I've told you. The geometric mean is the square root of the x times y, where x and y are the two outside numbers, and the missing number is the middle, mean, average, middle value. So we're going to take the square root of x times y. So we have 3 terms here, and we're missing the middle value, so we'll use geometric mean, where 4 is x and 16 is y. So substituting, I get the square root of 4 times 16, and I can break that up into the square root of 4 times the square root of 16. And I get 2 times 4, which is 8. But when you take the square root of a number, you got to be very careful. We have plus or minus. So the answer, the geometric mean here, is plus or minus 8. So that value there could be plus or minus 8. The last little part, we're going to look at what happens if I give you 3 blank numbers. 972, blank, 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 and 2. How would I use the geometric mean to find missing values? It's not too terribly bad. But notice how 972 is the first number and 12 is the last number. Okay? Well, that's the first and fifth. If you look at 1 and 5, the middle value is 3. So we can take the geometric mean of the first value and the fifth value to get our third value. So that's the square root of 972 times 12, which gives us 324. So this number here is 324. So to get this number, now I know the first and the third, 972 and 324. So I can take the geometric mean of 1 and 3, the first term and the third term, to get term number 2. So the square root of 972 times 324, that gives us 108. So 972, 108, 324, blank, and 12. I have 324 here and 12. My third and fifth term. If I take the geometric mean of 3 and 5, that would be my fourth term, which is what I'm missing. So that middle term was 324. So lastly, the geometric mean is the square root of 324 times 12 to get that fourth term, which gives us 36. So these 3 missing terms, 972, 108, 324, 36, and 12. So you can use the geometric mean to find multiple blank entries or terms in a sequence. You just have to look at which terms you're given. And if it's the second and the fifth, you find the halfway mark. Like we had one term, first term, and fifth term. Well, the middle value between 1 and 5, that's 3. We got the middle term. We took the geometric mean of term number 1 and term number 3. That gave us the 2. And 3 and 5, the geometric mean between those two terms, gave us that fourth term. So that's geometric sequences. In the last two sections of Chapter 9, we're actually going to look at what a series is for both geometric and arithmetic series. So if you have any questions or anything about the video, please, at the bottom of the YouTube page, just go ahead and ask your questions or email me. Thanks, guys.